Hi, I'm Zhang, and I will present our work, Faster and Cheaper Serverless Computing on Harvested Resources. This work is done with Microsoft Research. I'd like to start with a brief introduction to serverless computing and harvested resources in data centers. First, let's look at serverless. From the user's angle, serverless is an attractive abstraction with intuitive event-driven interface, pay-per-use pricing models, and users don't need to worry about VM management. The most popular shape of serverless, which is function as a service, is usually featured with bounded completion time and no persistent states between invocations. However, from the serverless provider's angle, providers do need to provision, manage, and pay IaaS provider for hosting VMs. This ties the cost of servers to the cost of underlying VMs. Even worse, serverless provider often needs to pre-provision a large amount of VMs to provide fast elasticity and the illusion of infinite capacity. Now let's look at harvested resources in data centers. Data centers are usually underutilized. The left figure shows the resource underutilization of a Google cluster. As a result, IaaS providers offer their surplus resources as VM at a much lower cost. And two examples of this are spot VMs, which are allocated with a fixed size, and burstable VMs that can briefly burst to their maximum size. Along similar lines of work, Microsoft recently introduced Harvest VMs as a more efficient and cheaper alternative. Harvest VMs are allocated with a minimum size, and they are able to grow and shrink to harvest all the unallocated resources on the host. The Harvest VM is only evicted if their minimum size is needed for regular VM. And before eviction, they get a grace period, which is, for example, 30 seconds on Azure. In order to reduce the operation cost of the underlying VMs and to provide a faster and more efficient serverless product, we propose to host serverless computing on low-cost Harvest VMs. To understand the challenge and feasibility of hosting serverless and Harvest VMs, as a first step, we need to perform a characterization study for both Harvest VMs and serverless workloads to see if they actually match. We'll start with characterizing Harvest VMs. For Harvest VMs, we mainly care about two things, which are VM eviction and VM resource variation. The reason is that VM eviction translates to reliability and resource variation translates to performance. The more frequent the resource varies, the harder it is to get stable performance. We use two different traces to study these two objectives. The private cluster trace described in the OSDI 20 paper for eviction analysis, and a smaller trace with resource allocation information for resource variation analysis. We first look at the VM lifetime, or in other words, how frequent Harvest VMs are evicted. The left figure shows the CDF of Harvest VM lifetime in the larger VM trace. We can see that more than 90% of Harvest VMs in the red region live longer than 1 day, and 60% of Harvest VMs, as shown in the orange region, live longer than 1 month. So, intuitively, most of the Harvest VMs are not short-living, and evictions are generally infrequent. Then let's look at the resource variation. We mainly care about harvesting CPUs, which are usually the scarcest resources on public clouds. The figure shows the CDF of Harvest VM CPU change interval. The CPU change interval refers to the duration between two consecutive changes of allocated CPUs on one Harvest VM instance. As shown in the figure, 70% of change intervals in the red region are longer than 10 minutes. 35% of intervals in the orange region are longer than 1 hour. Intuitively, compared to the VM evictions, VM resource variation is much more frequent. Thus, the implication is that in order to fully leverage the resources provided by Harvest VMs, proper load balancing is required. Now let's turn to characterization of the serverless workloads. For serverless workloads, we care most about the relation of invocation duration and VM eviction grace period. If an invocation is shorter than 30-second grace period, it can always safely terminate, while longer invocations are prone to failure. Thus, we call the invocation long invocation if it is longer than 30 seconds, and short invocation otherwise. In Azure Function, all functions are grouped into applications, and application is the unit of scheduling and resource allocation. Following the same logic, we classify applications to long applications and short applications, and long applications are the ones with at least one invocation longer than 30 seconds. These applications are prone to invocation failure if allocated on harvest VMs. For this analysis, we use a detailed trace of a small cluster with precise invocation time. We also validate the trends in the small trace against a large corresponding trace, and we refer interested readers to our paper for more details. The left figure shows the CDF of invocation durations in the serverless workloads. So 96% of the invocations in the right region are short invocations, so most invocations are short. However, if we examine the breakdown of the total execution time, it turns out that long invocations take over 82% of the total execution time. The intuition here is that the vast majority of the invocations are short, but long invocations take over most of the execution time, and in other words, long invocations take over most of the computation power, assuming homogeneous CPU usage. If you look at the trace from the applications angle, the trends are actually exacerbated. So 48.7% of applications turn out to be long applications, and these long applications take over 67.5% of all the invocations and 99.7% of total execution time. So long applications take over even more computation power than long invocations. The reason can be explained by the left figure, which shows the duration distribution of the long applications, where each point on x-axis corresponds to one application, and the arrow bar shows the standard deviation of durations. The average duration of many long applications are well below 30 seconds, and are still classified as long applications only because of a small fraction of long executions. In the end, the intuition is that nearly half of the applications are long, and these long applications take over almost all the execution time, and in other words, computation power. To summarize, the main takeaways from the characterization study are threefold. First, intuitively serverless workloads are a good fit for harvest VMs because most invocations are short and thus safe against VM evictions, and also because VM evictions are relatively infrequent. Second, harvest VM resource variation are much more frequent than evictions, requiring proper load balancing to fully leverage the resources. Meanwhile, there's still a good chance that we can deliver good performance for serverless workloads because harvest VM resources are relatively stable compared to invocation durations. Third, long applications take almost all the execution time. This has a huge impact on our eviction handling strategy, as we'll see in a few minutes. Since we are convinced that serverless workloads fit harvest VMs well, our immediate challenge is to eliminate or to minimize invocation failures caused by VM evictions. The natural idea is to use a mix of low-cost harvest VMs and reliable regular VMs, in which short applications can be allocated on harvest VMs to improve efficiency, and long applications can execute on regular VMs to guarantee reliability. To this end, we study three strategies that make different trade-offs between reliability and efficiency. And here, reliability refers to invocation failure rate, and efficiency refers to the fraction of computation hosted by low-cost harvest VMs. The three strategies are no-failure strategy, which guarantees zero failure rate, bounded failure strategy, which provides an upper bound on the failure rate, and lastly, the leave and let die policy, which has no theoretical guarantee on failure rate. The study is performed with tree-stream simulation, and we refer interested readers to our paper for the detailed simulation setup. So now let's look at the three different strategies. The first one is the no-failure strategy. It guarantees no eviction-induced failure by assigning all the long applications to regular VMs. In such a way, long invocations are never prone to VM evictions, where short invocations can safely terminate within the grace period. Since this strategy offers the best reliability, we are only concerned with the efficiency. Unsurprisingly, the efficiency is unsatisfying, with only 12% of computation hosted by harvest VMs. This matches the intuition from the characterization that almost all computation power are taken over by non-applications. It's also noteworthy that the fraction of computation hosted on Harvest VMs is actually larger than the fraction of total execution time occupied by short applications. This is because we also consider container keep alive when accounting resources. We also check that this ratio is not sensitive to the actual length of keep alive. So we've seen that offering 100% reliability is expensive. So let's look at the bounded figure strategy, whose intuition is that if we are willing to tolerate a small fraction of eviction failures, we can allocate more applications to Harvest VMs. This strategy provides an upper bound on failure rate by bounding the failure rate of each application. If you want to bound the failure rate by 100 minus X%, we check the X duration percentile of each application and assign the application to regular VM if the value is longer than 30 seconds. For example, to bound failure rate by 1%, we check the 99th percentile of each application. In the worst case, that all the non-invocations on Harvest VMs fail, we get 1% failure rate. Because every application on Harvest VMs has at most one invocations being non-invocations, the application and applications on regular VMs are always safe. Since we have a well-defined upper bound on failure rate, we ask the same question on efficiency. The right figure shows the fraction of computation power hosted by Harvest VMs when we switch the decision percentile X from 95 to 99.9. Essentially, bounding the failure rate by 1% allows 45.7% of computation to be hosted by Harvest VMs, as shown in the yellow circle. Bounding the failure rate to be less than 0.1% allows 28% of computation to be hosted by Harvest VMs, as shown in the red circle. In summary, although efficiency improves compared to no failure strategy, it is still pessimistic, because according to our characterization of application duration distribution, most invocations that run in regular VMs are still short. Lastly comes the leave and let die policy, which allocates all the applications to Harvest VMs. This strategy is clearly the most efficient, but lacks a theoretical bound on failure rate. So this time we ask the question of reliability. To understand the actual failure rate, we simulated two Harvest VM traces. One is the worst case trace with maximum VM eviction rate, and the other is a typical case with closest to average VM eviction rate. The number of VMs over time in the two traces are shown in the right figure. The actual invocation failure rate turned out to be very low. In the worst case, the serverless platform achieves 4 nines of reliability, and in the typical case, it achieves 7 nines of reliability. The actual invocation failure is low because failure requires two low probability events to happen simultaneously, which is that a Harvest VM gets evicted while it is running a long invocation. To summarize, the no-failure strategy is very conservative and causes most of the computation to be hosted by regular VMs. Bounded failure strategy improves the efficiency, but is still pessimistic. The leave and let die strategy, although lacking a theoretical bound on failure rate, actually delivers the best efficiency and low failure rate. As a result, in the rest of this presentation, we will stick to the leave and let die policy. As mentioned in the characterization, the frequent resource variation of Harvest VMs implies that proper load balancing is required for good performance. We use join the shortest queue as the start point of our load balancing design. That the load balancer chooses the VM with the least pending work to allocate an incoming invocation. And the pending work is approximated by weighted sum of CPU and memory usage. Although join the shortest queue optimizes queuing and execution time, it can lead to high cold start rate when the number of backend VMs is large. Cold start is common for all the serverless platforms, that a container or something similar needs to be provisioned and the runtime needs to be loaded before an invocation can execute. And cold start typically takes 0.2 seconds to a few seconds. Join the shortest queue increases cold starts because invocations of the same application are distributed across all the backend VMs, making the interarrival time longer than the container keep alive, which forces each invocation to be a cold start. To optimize the cold start, we propose a new load balancing algorithm, the mean worker set algorithm. The intuition is that we can consolidate each application to a minimum set of backends. Thus, the interarrival time is minimized, leading to more warm starts, while at the same time, the queuing time can still be reduced. The algorithm proceeds as follows. For each application, the load balancer estimates its expected resource usage. It also hashes the application to a home VM as the initial worker set. And then the load balancer continues to add VMs to the worker set until getting adequate resources to satisfy the expected resource usage. Eventually, the load balancer chooses the least loaded VM in the worker set to allocate the invocation. Besides, we adopt consistent hashing to minimize reshuffling of home VMs upon VM eviction and redeployment that can lead to change of number of VMs in the system. We implement the proposed algorithm on OpenWhisk, an open-source serverless platform developed by IBM. The architecture of OpenWhisk is shown in the right figure, and the dotted lines highlight our changes to the system. Specifically, in each invoker, we add a harvest monitor that collects resource information and VM eviction signals. The controller is modified to maintain data from harvest monitor and also implements the mean worker set algorithm. We also introduce a separate module in the control plane, the resource monitor, which tracks resource variation in the system and spins up new VMs to maintain available resources. So now I'll briefly go over the evaluation. More details on the evaluation setup and more evaluation results can be found in the paper. We deployed OpenWhisk on Azure with one controller VM and invokers deployed on both regular VMs that emulate Harvest VM traces and actual Harvest VMs. We use function bench and synthetic CPU-intensive functions as the workload. First, we evaluated the benefit of the mean worker set load balancing algorithm. The figure on the left shows the 99th percentile latency of mean worker set during the shortest queue and vanilla OpenWhisk across different user request RPS. The right figure shows the cold start rate of mean worker set and they join the shortest queue. Essentially, mean worker set achieves 22.6x throughput of vanilla OpenWhisk and 1.6x throughput of join the shortest queue. The improvement over join the shortest queue comes from reduction of cold start, that the mean worker set reduces cold starts between 56% to 76% compared to the join shortest queue. We also evaluate the performance benefit of Harvest VMs by comparing the performance of the serverless platform on Harvest VM versus on regular VMs under the same cost budget. We tested multiple price configurations as shown by the table on the right, in which D-evict refers to the discount ratio of base evictable cores, and D-harvest refers to the discount ratio of harvested cores. The baseline configuration is just the regular VM. The lowest configuration has the lowest eviction discount, and also a harvest discount equals that is identical to the eviction discount. The typical to the best configurations have different eviction discounts described by their names, and they all have a harvest discount that are larger than their eviction discount. The performance of different configurations are shown on the right figure. Essentially, Harvest VMs achieve 2.2x to 9x throughput compared to baseline. Lastly, we also compare Harvest VMs to spot VMs, which are alternatives that leverage surplus resources. The right figure shows the comparison of Harvest VMs against spot VMs, and in clockwise direction, the invocation failure rate, cold start rate, normalized price, and the fraction of idle capacity that are leveraged by different VM types. Each point on the x-axis corresponds to a different VM type. For example, H2 refers to Harvest VM with 2 base CPUs, and S2 refers to spot VMs with a fixed size of 2 CPUs. Essentially, Harvest VMs are better than spot VMs in multiple dimensions. So first, Harvest VMs are more reliable. Invocation failure rate on S2 is 23.2x as H2, as shown by the red circles. Second, Harvest VMs leverage more idle capacity. H2 leverage almost 100% of the idle capacity, while S2 leverage only around 92%, as shown in the red circle. Third, Harvest VMs are also cheaper. The amortized CPU price of H2 is 33% less than S48, which is the cheapest of all spot VMs, as shown in the green circle. So this concludes our talk. To summarize, we propose to host serverless platforms on harvested resources. We quantify the challenges of using harvested resources for serverless invocations, including harvest VM evictions and resource variation. We demonstrate the reliability of hosting serverless workloads on harvested resources, and we also demonstrate the performance and economic benefits of hosting serverless platforms on harvested resources. This is the end of my talk, and thank you for your time.